Last time we built a CPU. It can fetch instructions from memory, decode them, and execute them. But it always runs the same sequence. Start at address 0, go to 1, then 2, then 3. What if we want to repeat something? What if we want to skip ahead based on a result? Our CPU needs to make decisions. Let's teach it how. We need a new instruction. The jump instruction. Instead of incrementing the PC by 1, we load a new address into it. When the CPU executes jump, it doesn't increment the PC. It replaces the PC with the jump address. Let's see it in action. Here's a program at addresses 0, 1, 2, and 3. Address 3 contains jump to 0. Watch what happens. The PC goes 0, 1, 2, 3, then back to 0. Then 1, 2, 3, 0 again. We just created an infinite loop. The program runs forever. But an infinite loop isn't very useful. We need to jump conditionally. Remember the status flags from when we built the ALU? The 0 flag is set when the result is all zeros. The negative flag is set when the result's top bit is 1. These flags tell us something about the last operation's result. What if we could jump only when a flag is set? But how does the CPU actually check the flag? It turns out that conditionals are just gates. Here's how a conditional jump works. The control unit asks, is this a jump if 0 instruction? And the flag register has the answer to, is the 0 flag set? An AND gate combines these signals. If both are true, the output says, jump. This signal controls a multiplexer. The MUX chooses between PC plus 1 or the jump target. The CPU doesn't decide, it just follows the gates. Here are some conditional jump instructions. JZ jump if 0. J and Z jump if not 0. J and jump if negative. The CPU checks the flag. If the condition is true, it jumps. If not, it just increments the PC as usual. Let's build a countdown loop. Address 0, load 5 into register 0. Address 1, subtract 1 from register 0. Address 2, jump to address 1 if not 0. Address 3, store register 0. Watch it run. Register 0 starts at 5. Subtract 1, now it's 4. Not 0, so jump back. Subtract 1, so R0 is now 3. Subtract 1, so R0 is now 2. Subtract 1, so R0 is now 1. Subtract 1, so R0 is now 0. The 0 flag is set, so J and Z doesn't jump. We fall through to address 3. We just built a loop. It repeats until the counter hits 0. So far, we've been loading values directly into registers. Load 5 means put the number 5 in the register. This is called immediate addressing. The value is right there in the instruction. But what if we want to load from a memory address instead? Direct addressing, the instruction contains a memory address, and we load from that location. Load from address 10 means go to memory location 10 and get whatever's there. There's even indirect addressing. The register holds an address, and we load from wherever that points. If register 1 contains 10, then load from register 1 means read from address 10. Why does this matter? It lets us write flexible programs that work with different data. We can process a list of numbers at different memory locations without changing the code. Let's put it all together with a real program. Find the sum of 3 numbers. Memory address 10 holds 5. Address 11 holds 3. Address 12 holds 7. Address 0, load from address 10 into register 0. Address 1, add from address 11 to register 0. Address 2, add from address 12 to register 0. Address 3, store register 0 to address 13. Loading from memory 0, so register 0 equals 5. Then adding 3 to 5 is 8. Then adding 7 to 8 is 15. Stored to address 13. We just ran a program that adds 3 numbers from memory and stores the result. But notice something. We've been cheating a little. We wrote load, add, store, not actual binary ones and zeros. And what if we could also use names for addresses too? Call them num1, num2, num3, and some? This shorthand we've been using, that's assembly language. And that's where we're headed next. From a handful of simple instructions, we can build any program. Loops, conditionals, data processing. The machine code is just bits, patterns of 1s and 0s. But it's hard to read and write raw bits. We need a more human-friendly language. Next time, assembly language. Human-readable code that maps directly to machine instructions.